Hello, my name is Mario Mamalis. Welcome to my screencast about Azure PaaS Microservices. My goal is to demonstrate a semi-realistic scenario of a software system containing microservices utilizing Azure Platform as a Service. Most of the materials on the internet regarding microservices developed on Azure are about service fabric or containers. There is, however, a third approach that we can take, and that is with PaaS services, such as web apps, Azure Functions, and Logic apps. In this screencast, we will dive deeper into developing services with Azure PaaS and learn a few tips and tricks that I discovered along the way. I hope that you find this subject as interesting as I do, and hopefully you can use some of the lessons learned in your own projects. Let's go over a brief outline of this screencast. First, we will talk about some prerequisites for those who are interested to develop a similar solution. We will then have a brief overview of microservices and the problems they are meant to solve. Then we'll go over the architecture of the sample solution we will be developing. We will create the initial resources needed through the Azure Portal. We will create the solution in Visual Studio, which is a preferred development environment for .NET and Azure development. We will then develop the admin console application that will calibrate certain resources and seed some sample data. We will develop the client console application that will simulate a user interacting with our microservices. We will develop all the PaaS microservices using web apps, Azure Functions, and Logic apps. We will deploy all the PaaS microservices to Azure. We will then develop a wiretap app that will help us visualize the journey of user actions as they travel through the PaaS microservices to achieve the intended goal. And finally, we will recap what we accomplished and highlight the most important points.
Before we look at the prerequisites, it's important to note that all the code that we'll develop and demonstrate in this screencast can be found in this GitHub repository. Please feel free to go and clone this repository and use the code for your own purposes, either to experiment with or borrow some ideas and some code for your own projects.
In order to be able to develop a similar solution in a similar fashion, you will need the following: an Azure subscription, which can be created for free by following the directions on the link provided. You can use a development environment of your choice. However, I strongly recommend using Visual Studio 2017 version 15.4 and above. Visual Studio is tightly integrated with Azure, simplifying development, deployment, and troubleshooting of Azure resources. Finally, you will need Azure Storage Explorer, which will allow you to easily view the data inserted by the microservices into Azure tables. In this section, we will have a brief overview of microservices. We will look at what problems a microservices architecture addresses. We will take a look at the most important microservices design principles. And finally, we'll briefly review all the Azure options for developing microservices. Before we can talk about microservices architecture, we should understand what problems it addresses. Most applications that exist today have been architected with some degree of variance based on the monolithic architecture. Typically, we see a user interface, a middle tier, and database tier all being part of the same application. The middle tier may contain several different logical groupings that address different business domains. As an example, an online shop application may have different middle tier domains such as order processing, payment processing, inventory maintenance, and customer support. All these domains are tightly coupled together, usually interacting with one database. As the application grows with time, so does the complexity and coupling of the tiers. Eventually, applications become so large and tightly coupled that maintenance becomes very costly and risky. The tiers and logical domains are neither reusable nor individually scalable. This clearly becomes problematic, especially for large-scale applications with high demand and frequent changes. Using the same example as before, an online shop developed based on a microservices architecture may look like this: a user interface application clearly separated from the business domain services of order processing, payment processing, inventory maintenance, and customer support. These individual apps have their individual databases, forming complete and separate components that address only specific business problems. Although communication between the services can be direct point-to-point communication, it is strongly recommended that it is accomplished through a message broker indirectly. This decouples the system even more and provides flexibility to swap services in and out as needed. It is also recommended to organize and expose all the service endpoints through an API gateway, especially for external-facing services. Our system is now more granular and its services can be developed, deployed, scaled, and maintained separately. Moreover, these separate services can now be shared easily by other applications. As with every type of architecture, the degree of conformity to specific rules is up to us. In the case of microservices, it is important that we follow certain design principles in order to get the maximum benefit. Microservices should be domain-centric, addressing and performing actions only for specific business domains, single-focused, doing one thing and one thing only, decoupled from each other with indirect and asynchronous channels of communication, autonomous, meaning individually deployable and scalable, resilient with the ability to fail gracefully, having mechanisms in place for retry logic and the ability to pick something up where it was left off, and observable through centralized monitoring and logging mechanisms in order to monitor health and address problems quickly. As we have mentioned in the beginning, this screencast is about developing microservices on Azure using PaaS. Regardless, I think it is a good idea to spend a few minutes looking at other options we have available on Azure. One option is using Service Fabric. Azure Service Fabric is a distributed system platform that makes it easy to package, deploy, and manage scalable and reliable microservices. Service Fabric also addresses the significant challenges in developing and managing cloud applications. Developers and administrators can avoid complex infrastructure problems and focus on implementing mission-critical, demanding workloads that are scalable, reliable, and manageable. Service Fabric is a technology best suited for very complex systems with very high usage requirements. It is, after all, the foundational technology powering core Azure infrastructure, as well as other Microsoft services such as Skype for Business, Intune, Azure Event Hubs, Azure Data Factory, Azure Cosmos DB, Azure SQL Database, Dynamics 365, and Cortana. Although it is possible to run a Service Fabric cluster on premises and even on competitor cloud platforms like AWS, I would rate Service Fabric as a technology with medium portability. I highly doubt anyone would actually run Service Fabric solutions on anything else but the Azure cloud. Another option is using containers. Containers have become very popular in the software development world. The idea is that all the code and dependencies are packaged in a lightweight container that can be developed and scaled individually without having to worry about operating systems and other VM complexities. They are particularly beneficial for when developers want the scalability control of infrastructure as a service, but simplified management and DevOps like platform as a service. With high level of control comes higher responsibility. Developers are responsible not only for the development of the containerized applications, but also for setting up the orchestration of the containers, making this the most complex option of the three. Azure offers different flavors and degrees of flexibility and control through different container services. Containers are, however, the most portable in terms of developing microservices and applications in general. You can easily lift and shift them to any environment, and you can even develop each containerized service using completely different technologies. And finally, what we will be using is platform as a service services. This option of developing microservices includes using web apps, API apps, Azure Functions, and Logic apps. Each app can easily be developed and deployed individually and scaled manually and automatically. In the case of Azure Functions, developers can develop and execute just the code we need for the problem at hand without worrying about the infrastructure to run it. As this is a serverless offering, Azure handles scaling automatically based on demand. The best part is that you only pay for the code that you're running, making this also the least costly option. Azure Functions can become microservices with each function acting as a particular endpoint. Azure Functions come with a variety of bindings and triggers to other PaaS services, making them the easiest to set up and stitch together. This is, however, the least portable option as it is very tightly bound to the Azure cloud. As I have mentioned before, I will be focusing the screencast on developing PaaS microservices, but it is good to know that we have many options. So let's have a quick recap of what we learned in this section. We compared monolithic to microservices architecture and we saw the problems that the microservices architecture addresses. We examined microservices design principles, and we reviewed different Azure options for microservices. In the next section, we'll examine the solution architecture for the application developed in the screencast. In this section, we will go over the architecture of the software system we will build to showcase PaaS microservices. First, we will define the microservices. Then we will examine the communication path to and within the system. We will explain the async request response pattern and why we will use it. And finally, we will identify the Azure PaaS types we will use to develop our microservices. So let's go over our sample solution architecture. The system we will build will be an online shop. It will be a semi-realistic scenario, enough to show the most important aspects of PaaS microservices. In other words, we will be building a POC because building a full production level system is obviously time prohibitive. Our entry point to the microservices will be the online shop API. This will contain the external facing endpoints to initiate an order of online products. Internally, the system will contain an order service, an inventory service, a payment service, and an email service. For this POC, we will use the same Azure Table Storage account with specific tables dedicated to each microservice. Now let's see a complete data flow through our system. In order to provide an asynchronous communication channel for our microservices, we will create 4 Service Bus topics. The topics will be Create Order topic, Check Inventory topic, Inventory Check topic, Payment Process topic. These topics represent the logical steps required in order to complete an order. There could be more steps in a realistic scenario, but for a POC, these will suffice. The process of placing an order to our online shop begins with a user, which in our case will be interacting through a console app, initiating an order through the externally facing online shop API. The API will insert a message in the Create Order topic. The order service will be listening for messages on the Create Order topic and will automatically receive any new messages placed in the topic. It will deserialize the message, perform the necessary actions such as inserting the order details in the order table, and it will then insert a message into the Check Inventory topic, since the next logical step is to make sure that there is enough inventory for the order products. The inventory service, which is a subscriber listening to the Check Inventory topic, will retrieve the message, check the inventory for its order product, and finally insert a message into the inventory check topic with the result of the performed action having 2 possible outcomes, either sufficient or insufficient inventory. Regardless of the outcome, the order service will retrieve the message and update the order details in the database. In case the outcome is insufficient inventory, the email service will retrieve the message as well and will send an email to the user with a status. It is important to note here that the subscription of the email service to the inventory check topic will be a filtered subscription. This means that only if the outcome is insufficient inventory, the message will be received and the email will be sent. The flow would stop here. The order service, having processed the message regardless, has recorded the final state of this order. In case of the outcome being sufficient inventory, the email service will not get the message, but the payment service will, and continue the flow by attempting to process the payment. It will then insert a message into the payment process topic with the outcome of this action. In similar fashion as before, the order service will receive the message regardless of the outcome and update the order details. If the outcome is payment succeeded, the inventory service will retrieve the message as well and update the inventory since the order has cleared the final step. Simultaneously, the email service will retrieve the message regardless of the outcome and send an email to the user that placed the order with the final status. At this point, we have completed a full journey through our system. The communication path is completely asynchronous, decoupling all the services. What this also means is that the user does not know in real time what happened to the order. The best we can do in this case is display a message to the user as soon as the order is placed. When the order is finished, an email will be sent confirming the final status, which can be either failed or succeeded. So what if our specs for the user application specify that the user has to get a real-time message on the client app showing the outcome of the order? There are 2 ways we can accomplish that. One way is to create a separate synchronous path with point-to-point communication between the services. This is doable, but not recommended, since it would break one of the best practices we have defined in the previous section. The second and preferred way is to implement the async request response pattern. Here's how this will work. When the user places the order to the online shop API, a flag will be included in the order that will indicate that a real-time response is required. The online shop API will see that flag and it will create a transient response queue named with the order GUID in order to ensure uniqueness per request. The rest of the flow will remain the same. As soon as the order service gets a message indicating that the inventory is insufficient, or the payment failed, or the payment succeeded, it will insert a message in the transient queue with the outcome. The online shop API endpoint, which is still open, as the user is expecting a response, will retrieve the message from the queue and return the response with the order status. And there you have it. We have now achieved both an asynchronous communication path and a real-time response to the user without breaking any best practices. In order to build this system, we will utilize several PaaS offerings. The online shop API will be developed as an API app. The order, inventory, and payment services will be Azure Functions. The email service will be a logic app. The messaging mechanism will be Service Bus topics. And for storing data, we will use table storage. So let's recap what we did in this section. We visualized the solution architecture. We examined the process flow. We understood the asynchronous request response pattern. We identified the Azure PaaS types used. In the next section, we will create the initial resources in the Azure Portal. In this section, we will create the initial resources on Azure. We'll create a resource group. We'll create a Service Bus namespace. We'll create all the Service Bus topics that we will need. And we'll create a storage account. We are here at the Azure Portal dashboard where we can begin adding resources. There are a few different ways to create resources on Azure. You can browse popular categories of resources on the left navigation bar, which can be customized to show the categories you mostly use. You can click New and select from a full list of categories, or you can type the name of the resource type you're looking for and filter the selection to pick what you need. I will type and select Resource Group. Here we see a short description of what a resource group is. To create a resource group, we will need a unique resource group name, a valid subscription, and a resource group location. I'm going to go ahead and create it. I'm going to pin the resource group to the dashboard. And now we're ready to start creating resources. So first we're going to create a Service Bus instance. We need a unique name for the Service Bus namespace. We're going to leave the rest of the selections the same. I'm going to go to the dashboard. And we see that we have the Service Bus instance created under our resource group. I'm going to open that. And we're going to create some topics, actually all the topics that we will need for our microservices solution. Create order topic. I'm going to enable duplicate detection. I'm going to leave everything else the same. sec inventory topic. Inventory checked topic. And finally, payment process topic. Now we have our topics for the service bus, and the last thing we need to do for now is to create a storage account. The naming convention is slightly different than the other resources because Azure only allows characters and numbers for storage accounts. Everything else we should leave as the default. For resource group, we must select the same resource group that we selected before. Remember, we need to have all the resources in the same resource group so that we can easily manage them. I'm going to create the account. Okay, our storage account was deployed. We're going to go ahead and look at the resource. So our storage account is a generic storage account that offers blob storage, file storage, tables, and queues. For our purposes, we will use the tables where we will store data that microservices will insert. So to recap what we've done so far, we gained some experience of the Azure Portal. We created a resource group. We created a Service Bus namespace with several topics, and we created a storage account. In the next section, we will create the initial solution in Visual Studio.
In this section, we will create the initial solution in Visual Studio. Our first project will be an admin console app that we will use in order to populate certain data and create our filter subscription rules. In order to accomplish that, we will need to install a few NuGet packages that will allow us to interact with Azure Storage and Service Bus. We will create classes which we will name table entities in order to populate them with data and insert the data in Azure Tables. We'll then run the console app and seed the data. And then finally, we'll create filter subscription rules and run the console app once again so that those filter subscription rules are created on the Service Bus.
First, we'll create the admin project, which will be a console app. We're going to use this project to seed some data and also calibrate certain Service Bus topics later on. First thing we're going to do is going to create we're going to install all the NuGet packages. We will need a NuGet package for interacting with the Service Bus. Next NuGet package will help us interact with Azure Storage Tables. And finally, we'll need the configuration manager for Azure. Okay, now we have the NuGet packages. We'll go ahead and create the table entities that will represent the tables on Azure Storage Tables. We'll create a customer entity. And here we have to define the partition key and the row key Partition key and row key are required to identify a unique row in Azure Tables, and for this we will use region as a partition key and customer ID as the row key. Those are properties that are exposed by the table entity base class. Okay, we have our customer entity. Next, we're going to create the product entity. So I worked through spacetime really fast, and we can see we have a product entity and an inventory entity ready to use. I'm going to add some asynchronous programming capabilities to our program class. Okay, and then I'm going to add a method so that we can seed our tables. We will need a storage account object to connect to our storage account. Here we're using the NuGet packages that we installed before. And we will need a table client in order to be able to interact with our tables. The storage account connection string, we're going to retrieve it later from the Azure Portal. And we'll create two more methods. One to seed the customers, and one to seed the products. All right, let's go to the portal and get the connection string.
We're here back at the Azure portal. We're going to grab the Azure storage account for our table storage. Under access keys, we have key 1 and key 2. We're going to use key 1 and we're going to grab the connection string. All right, let's go back to the project.
We'll go to the app settings and add a key for the Azure connection string. So here's the final version of seed customers. We're populating 3 rows using the table client. Similar fashion, we're populating a few products and some inventory records. I have to make a quick change. I need to replace decimal and make it a double. Azure tables don't work with decimals very well. Actually, they don't work with decimals. So I need to update the code here to reflect that these values are doubles. And before we insert the seed data to the tables, we have to create the tables on the portal. Going back to the storage, go into our tables, and we're going to add 3 tables. Great. Now we can make sure using our storage explorer that those tables are there. And there they are. And let's run the console app so that we can see the data. All right, let's check. Refresh, and there are our rows that we inserted for product, inventory, and customer.
Before we move to the next part of this section, which has to do with Service Bus topic subscriptions, I think it's good to visualize what these subscriptions will be. So in order to be able to process all the messages that will originate from the online shop API, all our services have to subscribe to the topics. So as part of the next section, we will create the following subscriptions. Create order, check order inventory, update order, process payment, send email, update order, this time attached to the payment process topic, update inventory, and another send email subscription, this time attached to the payment process topic. So it's good to point out here that the subscription names have to be unique per topic. That's why we can have send email and send email again, because they belong to different topics. Another good point to make here is about the filter subscriptions that we've talked about before. So these filter subscriptions mean that the messages will be delivered to the corresponding services only if certain conditions are met. So we'll not be processing the payment if the inventory service determined that there is not enough inventory to process a payment. Now, as I said, the subscriptions themselves we're going to create through the portal, but the filtering rules on those few filter subscriptions we're going to have to create programmatically, because that functionality is not yet available through the portal.
All right, now that we have visualized the subscriptions, we're going to go ahead and create them on the portal. Check inventory topic first. We will need one subscription. Create order topic, one subscription. Inventory check topic will have 3. And those checkboxes I'm checking here are about messages that have expired or that have caused a filter evaluation exception. We're moving those messages to the dead letter subqueue, and I will go over what that means later on. Okay, now we have all our subscriptions created. We'll grab the Service Bus connection string. We will need it in our code. So under shared access policies, we are going to use the default policy that is already created for us. We'll copy the primary connection string, and under app settings, we'll add another key. So I went ahead and created a few more keys for the topic names and subscription names. And then let's go back to our program. We need to add a new method to create the subscription rules for the filtered subscriptions that we mentioned before. So for this, we'll have to create a new subscription client object. One for each subscription that will contain filters. So this is for the process payment one. First, we'll provide the Service Bus connection string. Then we will provide the topic name. And finally, the subscription name. And these 3 values identify a unique subscription. So I went ahead and finished the code so that you don't have to watch me type. As you can see, we have 3 subscription clients, one for each filtered subscription. And then we have code that cleans up the default rule and adds a specific rule for each subscription. So why did we remove the default rule? The default rule, which is added by default when you create a subscription, is a Boolean filter, which means that if it's true, all the messages will be delivered. If it's false, none of the messages will be delivered. So when it's created by default, it's set to true, and we want to remove that because we want to filter those messages based on our rules. In order to remove a rule, first we check if the rule exists and then we remove it. And in order to add a rule, first we check if the rule does not exist and then we add it. Let's look at what a rule description is. So a rule description has a unique name and it has a filter. In our case, we're using a correlation filter. This means that the filter corresponds to the correlation ID of the message. And adding a rule means that the message will only be delivered to the listener if the correlation ID matches a specific value, such as verified or insufficient. Service Bus supports Boolean filters and SQL filters in addition to correlation filters. Boolean filters are either true or false, and SQL filters hold a SQL-like conditional expression with more complex logic. So I commented out the code that seeds the tables because you already have the data, and I'm going to run the program just to create the subscription rules. Okay, subscription rules created. Let's do a spot check and see if actually one of the rules is in our topic. For that, we will call the method that's provided by the client, which is getRulesAsync, and we'll browse the properties. And here we can see that under filter, we have a correlation ID of verified, and our rule has been successfully created.
So let's summarize what we did in this section. We created the admin console app. We installed the appropriate NuGet packages in order to be able to interact with Service Bus, Azure Tables, and take advantage of the configuration manager. We created the necessary table entities. We seeded the data for customers, products, and inventory. We created subscription rules for our filtered subscriptions. And in the next section, we will develop the online shop API and also the client console app that will interact with that API. So let's take a look what we will accomplish in this section. We will create the order API. We'll configure a Service Bus connection. We'll develop the order post endpoint in order to create an order. We will create a client console app. We will invoke the order post endpoint from the client console app. And finally, we will verify that the order messages are inserted in the create order topic. For the service API that we'll expose to the client, we will create an ASP.NET Core Web API app. And to begin, we will need a few models to represent an order and its related classes. We'll begin with a customer class. We have an ID, first name, and after some space-time warping, we have the classes that will represent an order. We have a customer, an order, a payment, and a product. These classes look familiar because they expose the same properties as the table entities we used in the admin console app. However, these classes are not going to be directly used to insert data. These will be used to create Service Bus topic messages. Next, we need to add a few app settings. In ASP.NET Core, app settings are slightly different than a regular .NET application. The settings are defined in a different way. In core, there's an app settings JSON file that holds the settings, and we will add a setting for Service Bus connection string and one for the order topic name. For the connection string, we can use the same connection string that we use in the admin app. And we know the name of the topic is create order topic. So in order to use these settings programmatically, we must create an app settings class, and we will bootstrap this class to the application when it starts. So in this app settings class, we add the corresponding properties to reflect our app settings, service bus connection string, and order topic name. Then we'll need to modify the startup.cs class in order to make our app settings file visible to the core. Using the configuration builder, we will supply a base path for the location of our files based on the environment. And then we will add the app settings.json file. And also an additional line that adds what it seems to be the same file, but it is actually to tell the core to first load app settings.json and then a settings file of the same name, but with the current environment as part of the file name. What this will do is we'll load the appropriate settings based on the environment, and the environment could be dev, test, staging, or production. Of course, in this application, we'll just use the same settings, the same environment, but this is good to know for when you create a real application. So core uses an options pattern to resolve settings from app settings.json. And to read the settings from the configuration file, we will need to add some code to the configure services method to know where it's going to look at. And then we need to register the settings in the dependency injection container. Okay. So in order to use the options pattern in the controllers, we will first have to install an extensions option NuGet package. Okay, and then we're ready to, but first let's delete the values controller that was created by default and add our orders controller. We'll use a template that provides some boilerplate code. And when this finishes, we will see that we'll have quite a few methods already following the RESTful pattern. First thing is to make the app settings available. And now that we have the settings in the container, injecting them into a controller is as easy as using the options pattern to add into a constructor. So we inject an instance of iOptions with a generic type of app settings. And then we will add the code to the post method of the controller, since we will be creating an order. First, we need to change the input parameter to be an order. Then we'll create a topic client. And in order to do that, we'll have to install the Service Bus NuGet package. Remember, we have to install it for all the projects that will need it in the solution. And then we provide the Service Bus connection string and the order topic name from our app settings. Okay, and to create the message, first we add some code to check if the order parameter is actually there. If it's not there, we return a bad request, which is HTTP status code 400. And let's not forget to make our method return an action result. Then we create a Service Bus message. Using the appropriate libraries, we serialize that message into JSON. And then we create a message ID, which is necessary. All messages must have a message ID. For that, we use a GUID, which we convert to string. Then we send the message to the topic asynchronously, and we return a 200, indicating that everything is okay. If there is an exception, we return a 500 internal server error to the caller. And finally, we close the topic client. So, although we have what we need to call our service, I will also add another controller just to be able to display some text to know that our service is running instead of displaying a blank page. And here's the code I added. And as we can see, we return a content result that contains some HTML telling us that the service is actually running. Final step is to set the launch URL in launch settings.json file to point to the start controller that we just created. And then we go ahead and run the service. And we can see that the service is running successfully. Now we're ready to create the client console app and create an order. All right, let's go ahead and create the client console app. The first thing we need to do is to replace the reference to the HTTP client that comes out of the box with a new one through NuGet Manager, along with a few more packages. The formatting extension package provides a few more methods that will be useful to us. All right, then we create a helper class that will be used to make the requests to the API. We need the access to the HTTP client, of course. And before we can complete the code, I time traveled really quick and added our well-known by now model classes. And the post as JSON async is the additional method I was looking for. We supply the order and the URI to the endpoint, which is still on my local host. Now let's examine the code I already added in the program class. In the main async method, we prompt the user to press enter to place an order, and then we wait for the response in the process input method. In the process input method, we call the create order method, and right before we send the order, we display a message that we're sending the order. We then send the order, and then we let the user know that an order has been placed with a specific order ID. The create order method contains code that populates the model with our data. Required response parameter will be ignored for now, and the IDs for the products are the same as the ones we used in the admin project when we seeded the product data. In essence, we're simulating a user that would typically use a web interface, selecting products and placing an order. Okay, let's make sure that we have both the client and the order API projects set to start, and let's run the code. We see the client console app starting and also the order API. And as soon as both are running, we hit enter in the console app and we place an order. The order was placed and we place another order right away. And now we jump to the portal, where we should see the two messages placed on the create order subscription of the create order topic. And there we can see that indeed our messages have arrived to the topic. Let's take a look at the design diagram to understand where we are in the process. We have created the client console app, and through the online shop API, we've placed a message in the create order topic. We're still in the beginning. So let's summarize what we have accomplished in this section. We created the order API. We configured the connection to the service bus. We developed the order post endpoint. We created the client console app. We invoked the order post endpoint from the client console app. And we verified that the order messages are inserted in the create order topic. In the next section, we will develop the order service Azure Function project. In this section, we will create the order service. As part of that, we will create a function app. We'll configure the Azure Table Storage and Service Bus settings. We'll develop the create order function. We'll run the code. We will confirm that the data was inserted in the tables, and we will confirm that the next message was inserted in the check order inventory topic. For the order service, we will create an Azure Functions project. And you will see this type of project under Cloud if you have already installed the Azure development workload in Visual Studio. And in order to organize our code better, we will create a functions folder, and we'll create our first function. Select the appropriate file type. And then we select the type of function we want to create, and this one is a Service Bus topic trigger function. So let's take a look at the signature of the function. The Service Bus trigger attribute specifies that the function is triggered by a Service Bus topic. And also in this attribute, we define the topic name, the topic subscription, the connection access right, and the Service Bus connection string. We will go ahead and modify the parameters to meet our needs. So first we specify the topic name, then the subscription name. We change the access right to listen, and then we specify the Service Bus connection string. We'll also change the message parameter, and we'll remove the log info code that was added. Okay, let's grab some connection strings that are needed. So first we need to specify the associated storage account. And for now, we will use a connection string of the storage account we have created in our resource group. We'll also add the placeholder for the table storage connection string in order to interact with the Azure tables, and a Service Bus connection string. We will use those later. And of course, the check inventory topic name, which we will use in order to place a message in the check inventory topic. Finally, we'll need to specify a local port in this function. And when this function runs, since we will have multiple functions running, we want to differentiate the ports manually so that our debugger works properly. Next, we create a folder for our models, and we begin by adding customer. And to save time, we jump to the future where we have all our models, customer, order, payment, and product. We also need a folder for our table entities. We will need to interact with the order table, the order product table, a payment transaction table, and a product table. And just let's quickly take a look at the code that I added. All these entities inherit from table entity. We provide the partition key and row key and all the necessary properties that we need. And let's not forget to change our decimals to double. And okay, we're back to our function. We start by creating a method that will insert data in the order and order product tables as soon as the function picks up a message from the create order subscription. First, we need to access the storage account. Then we'll create a table client instance. Here's our table client instance. And then we create our order entity. And we populate it from the order data, which we will extract from the message. We need the customer ID, the status, and the 2 dates. Then we get a reference to the order table in our table storage using the table client. Then we create an insert operation. And finally, we execute async method to insert the data in our table. Then we'll proceed to do the same thing for each product in the order. And this time we will be inserting data into the order product table. Exact same steps as above. The only difference is that we're executing it in a for each loop. Remember, we're simulating an order that has multiple products in it. And this data comes from the message that the order API already received from the client and already placed into the create order topic. Okay, so before we proceed with the code, in the main method, we need to install the latest Service Bus NuGet package. This is different from Windows.Azure.Service Bus. Okay, let's not forget to make our method async for good practice. Okay, and first we need to create a topic client that we'll need in order to insert the message in the next topic in the process, which is the check inventory topic. So inside a try-catch block, we'll begin to develop the rest of the code. So let's take a look at the code. First, we perform some data validations to make sure we have the necessary data. We check if the topic message is not null or empty. Then we deserialize the order, and we check if the order contains the properties that we're expecting. Then we supply the rest of the information for the order. We change the status to created. We refresh the dates, and then we call insert order, which inserts the data into the order table. Then we create a message, we serialize the order, and we pass that message to the next topic in the process. We make sure we catch the necessary exceptions, and finally we close the topic client. Before we run the code, we must retrieve the rest of the connection strings. So first we grab the connection string for the table storage. That's where we have our tables. And then we grab the connection string for the service bus. Okay, we also need to create the additional tables that we will be interacting. The order table, the order product. Remember, we created entities for all of those. And the payment transaction. Okay, everything looks okay. We're ready to run the code. And since we have multiple projects as startup projects, we'll see the client console app, the order API, and the order service function running together. Something's wrong with the function. Let's take a look. Okay, I know what it is. We have provided the wrong name for the topic subscription. We'll fix that and run the code again. Everything looks good this time. We place the order and we see the function being triggered and processing the message. We make memory note of that order ID. Back on our table storage, we refresh the order table and we see that the data was inserted with the same order ID. And under the order product table, we see 3 entries, 1 for each product. So our tables were successful. Now let's check the messages on the service bus. First, let's make sure that we have no messages lingering in the create order topic. And then we see that in the check inventory topic, there is a message waiting to be processed by the next function that we will create. Let's have a quick recap. In this section, we created a function app. We configured the Azure Table Storage and Service Bus settings for that function app. We developed the create order function. We ran the code, and we confirmed that the data was inserted in the tables and that the check order inventory topic received the next message. In the next section, we will develop the rest of the functions for our solution. In this section, we will create the additional functions that we will need in order to finish processing an order. And those services that we'll create will be the inventory service, the payment service, and additional functions that we will need in the order service in order to update the order status as it traverses through the rest of the services that we'll be creating as part of this section. Then we'll run the code. We'll confirm that the order processing completes successfully, and we'll confirm that the messages arrive in the payment process topic. Finally, when all the code has been created and we have confirmed that everything is running properly on the local machine, we will deploy the services to Azure and we will run the code pointing to the resources that we deployed to Azure. Before we look at the rest of the functions, let's take a look at where we are in the process. We have called the online shop API from the client app and we initiated an order. The online shop API endpoint has inserted a message in the create order topic, and our order service, which is an Azure function, has been listening to that topic. It picked up the message and it recorded the data in the orders table, and then it inserted the message into the check inventory topic. In order to save time, I created the rest of the function apps that we will need for our system. So now we have 3 function apps. We have the order service, we have the inventory service, and the payment service. The order service is the one we started from the previous section. We added 2 more functions in this one, which we will take a look at very quickly. But before we get into that, there's one more step I need to show you that you need to perform in order to be able to run all these functions as part of the same solution. So that is, if we remember in the local.settings.json, we set the local HTTP port to 7071. What we also need to do is go to the properties of each function app, and under debug, we need to insert this line of code and specify the port that we also specified in the local.settings.json. And this will enable us to run these functions concurrently and be able to debug them concurrently as well. So in the order service function app, I added 2 more functions in addition to the create order. These functions are update order inventory checked and update order payment processed. These correspond to, when looking at the design diagram, they correspond to the update order subscription of the inventory check topic and the update order subscription of the payment process topic. And we need those 2 subscriptions and the 2 functions that I created in order to be able to update the order that we inserted as part of the create order subscription. So if the inventory was checked, we need to know what the status of that operation was. If the payment processed, we need to know what the status is as well. Now, we don't have the other services update the order table because we want to keep each service separate. And as I explained in the beginning, for this screencast, I'm using the same Azure storage account, but best practices are that you have separate databases. In this case, we're just separating them just by having different tables that each service is interacting with. So the order service is going to interact with the orders table and the order product table. And that's why that's the service that updates the status. So looking back at the code, it's pretty much the same pattern that we followed in the create order. The only difference here is, of course, we're looking at a different topic and a different subscription, as we can see on the signature. And then we are updating the data instead of inserting the data. And the difference here is that instead of a insert operation, we use a replace operation. And you will get this code from the GitHub repository that I mentioned in the beginning. But that's pretty much it. And the update order payment processed is exactly the same pattern. It just listens to a different topic and a different subscription. And of course, it updates the order for the payment processed operation. So that completes our order service. It's pretty simple. And then we have the inventory service. In the inventory service, I have the check order inventory function and the update inventory payment process function. And the names are a little bit weird because we need to be able to differentiate. If you remember, each function points to a specific topic and a subscription. So I need to be able to understand from the name which topic and which subscription a function is working with. So that's why the names are a little bit long. But anyway, these the check order inventory function basically checks the inventory and make sure that we have enough product in order to complete the order. And that happens in the isInventory_verified method, where we get a table client and we get a reference to the inventory table. And remember, we've inserted some data through our admin console for each product there. We have 10 instances of each product. So it goes through the order, and the order we have placed has 3 products. It goes through the order and makes certain that the quantity is greater than 0. If the quantity is 0 or less than 1, then we return a false. And what this does is we create the orders, we insert the order status or update the order status with a different message. And if you remember, part of our filter subscriptions is that we're using the correlation ID. So if the inventory is verified, we enter the verified flag in the correlation ID. If it's not verified and it's insufficient, we enter insufficient. So what does this do? So when we look at the diagram again, checkout order inventory is what this function that we're just looking at is listening to. So if the inventory is verified, it inserts a message into the inventory check topic with a verified flag as a correlation ID. And this subscription will get this message only if the flag is verified. If it's insufficient, it will not get this, it will not be inserted in this subscription, so the payment will never be processed. However, the order subscription will get all the messages. It's not a filtered subscription. And that's why here we are listening to that in the order service to be able to set the appropriate status of the order, which will indicate that either that the inventory was sufficient or was insufficient. So back to the code. After we do our check, we create the message that goes into the next topic, and we send that message to the topic. Of course, we have our try-catch blocks in order to be able to log our errors and so forth and so on. The update inventory payment processed function corresponds to this subscription, which is also a filter subscription. And what this does is after a payment has been processed and the order is complete, we need to go back to the inventory service and update the inventory. So basically deduct the number of instances of products that we just sold. Same exact pattern, some are validations, and then the method that updates the inventory. And of course, in this function app also we have our models that we're already using in other functions, and the inventory entity, which is corresponds to the inventory table. And as we discussed before, the inventory service only needs to worry about that specific table. And in the payment service, we have the process payment inventory checked function, and that corresponds to the process payment subscription as we've seen before. And the process payment subscription will only receive a message and process the payment through the payment service if the inventory was sufficient. Same exact pattern. We check if the payment succeeded, and for now we're just returning true from a simulated method because we don't want to deal with actually processing real payments for the screencast. And we set the order status to the appropriate status, whether the payment was verified or the payment failed, and we send it to the next topic, which is the payment process topic. If the message came into the process payment subscription because it cleared the inventory check, the payment service will send a new message to the payment process topic indicating whether the payment succeeded or not. And based on that, we update the inventory as we saw before if the payment has succeeded. And the order service will always get the message whether the payment has succeeded or not in order to get an accurate order status. And of course, what we will do in the future is we're going to place a message in the send email subscription, and our email service, which will be a logic app, will send the email to the user. So for now, we've completed all the functions and function apps that we needed. and we're ready to run the code and see what happens. Before we run the code and place an order, let's make sure that the data is correct. So in the inventory table, in our looking at the Microsoft Azure Storage Explorer, in the inventory table, we see that each product has a quantity of 10. So we have enough inventory. There is no data in the order and no data in the order product, and of course no data in payment transaction. Also, let's make sure that in our payment process topic, which is the last topic in the process, we don't see any messages. What we expect to see, because we don't have the logic app created yet that will send the emails, any order that we place, we expect to see a message inserted and wait in the send email subscription for now until we develop the email service. So let's go back to the code. Again, we have to make sure that we have multiple startup projects. We need all our function apps and the order API and the client app to start simultaneously. So we'll go ahead and run the code. We see the functions and the client API, the client console app running. We also see the API, order API starting. Okay, we know that the order API is running. I'll minimize that and make some room. This is the order service. So this will be our first function app that will process a message. This is process payment. This will be the last. And this is the inventory service, and will be the second one. Okay, now that we have all our windows in order, we'll go ahead and place an order. We see the ID is D29, and we see the messages being processed as they go through each topic. So we know all our functions run properly. So we see that the order ID again, it starts with D296. We'll go to the Storage Explorer and we'll look at the order table. We see that the order was created, and we see that the last status is payment verified. So we know that it went through all the topics, all the appropriate functions, and the payment was verified. Now we expect to see 3 entries in the order product, 1 for each product, correct. And we expect to see a payment transaction entry with status verified. Now if we go to the Azure Portal, I'll refresh the page. And we can see that as soon as it refreshes, indeed we have a message waiting in the send email subscription, because there's nothing that we have yet to retrieve that message. But let's go ahead and place let's do another experiment here. Let's go to the inventory. Yeah, we didn't even check the inventory. The inventory, we can see that each product that was in the order has been, the quantity has been reduced by 1. So we'll go ahead and make the quantity 0 for one of these products that our next order will place. And the logic that I have, even if one product, there's not enough inventory for one product, the order is not processed. But of course, you could add additional logic and say, oh, okay, we'll place a partial order. But for now, this will do. So let's see what happens when we place another order. Let's open our Windows again and place another order. So we see only two functions, two apps processed the order. The third one, which is a payment process, never got the message, and we can verify that. So this order starts with 91F0. We'll go to Storage Explorer, back to the order table. We see the 91F0 order, and we see the status being insufficient inventory. Of course, we will have 3 more products for the order that was initiated. And in payment transaction, we'll only see the first order that we placed because the second order was never processed. And in our Azure Portal, we'll refresh the page again. So we see one message. It's still from the first order because the payment processed topic never received the message because we never processed the payment. But if we look at a different topic, the check inventory topic, I believe we have another send email subscription there. And this one has the second message, the second order that we sent. Because if we look back at the design diagram, this is the send email subscription that originates from the inventory check topic. We again enter a message here if the inventory was not sufficient, and the user will receive a different email than if the payment was processed and the order was successful. Okay, so pretty much we've proved that our system is working fine for now. All our functions are working, our logic is working. So the next step is to deploy those services, those functions to Azure and run it on Azure, because until now we've been running everything locally. In order to demonstrate the excellent integration Visual Studio has with Azure, we will create all our Azure resources and deploy the code all within Visual Studio. I am logged into Visual Studio using the same Microsoft account that I used to create my resources on the Azure Portal and pointing to the same Azure subscription. So we will start by deploying the Orders API to Azure. And in order for a PaaS API to run on Azure, we must have an app service. We have the choice to select an existing or create a new app service. And we'll create a new one since we did not create one on the portal before this step. We provide a unique and descriptive name to our app. We make sure that we have the appropriate resource group, which we had before. And we can also configure the app service plan tier right here and select what fits our needs. Okay, we create OK, and the provisioning and publishing of the code has already started. This usually takes a minute or so. So while this is happening, we should go and examine our resources on Azure. Okay, we see that the app service plan and the app service have been provisioned already. And let's take a look at the app settings on the app service. We're going to make some modifications to improve performance. Oh, and what happened right now, as we were transferred to a new browser window, is that the code finished deploying and Visual Studio automatically opened a new window to the newly created API app in order for us to see that it is up and running. I'll type the URL to our start endpoint to see the message. And yes, we can see that the API app is running. All right, next we need to enter a few app settings on our newly deployed environment. And our app settings should be unique to each environment, but to save time, we will use the same ones that we use locally. So we enter the service bus connection string. And the order topic name. Okay, now we can deploy our first function app. Again, a unique name, and FA stands for function app using my convention. We will use the consumption plan pointing to the same Azure region as all of our other resources. And function apps can run either in a regular app service plan where you define the tier and scaling rules, or in a true serverless fashion under a consumption plan with pay-as-you-go capabilities and Azure control scaling. So while this is deploying, let's check. Well, it's almost done. Let's check our resource group again. The function app has been created, but it looks like, well, we're trying to refresh the functions. It looks like the code is still being deployed. Let's wait a little bit. Okay, the code has finished deploying, and now we can refresh and see our functions. All right, here we also have to specify the application settings, which are also known as environment variables. And this is an important step that you must not forget to do, otherwise your functions will not work on the cloud. You can notice that for the storage settings, Azure has created dedicated storage instances for the function app in order to store the logs, etc. And the connection strings for those settings have already been set in the app settings. Okay, so I went ahead and deployed the other two function apps, and we can examine our resource group again. We see the storage accounts corresponding to the function apps, the API app, the function apps themselves, and the original storage account, and of course the service bus that we always had running on the cloud. Now let's copy the URL of the newly deployed orders API and make sure we point our client console app to that in order to run the code pointing to the Azure resources. All right, now that's done. We disable all projects from starting simultaneously, except the client console app. So we select a single startup project, we run the code, and we place the order. Okay, when we examine our Azure storage tables, we see that the order was created. Order products are there, and our transaction is there. And now let's take a look at the service bus. And we see that the messages are piling up in the send email subscription. For good measure, let's repeat with placing another order. Let's check the data, everything looks good. Okay, looks like everything was deployed and everything is running successfully. So in this section, we created the inventory service. We created the payment service. We created additional functions in the order service. We run the code from Visual Studio. And we confirmed that the order processing has completed successfully. We also confirmed that the messages arrived in the payment process topic. And we deployed the services we created to Azure. In the next section, we'll create the email logic apps. So in this section, we'll create the logic apps we need in order to send the emails to the user. We'll create the payment processed email logic app. We'll create the insufficient inventory email logic app. We will run the code, and we'll confirm that the emails are coming through properly. We have seen the Service Bus messages piling up in the payment process topic because there are no listeners to process the next step, which is to send emails. For our email services, we'll create 2 logic apps using the Azure Portal so that we can see a different way of creating Azure PaaS resources. Logic apps provide an elegant way to connect services with other apps, such as an email client, and create workflows without writing code. In our resource group, we click Add and search for a logic app. We provide a unique name, and the name will be descriptive enough to differentiate this logic app that will handle the payment processed emails from the other logic app, which will handle the insufficient inventory emails. We select the same resource group and click Create. Once the deployment has finished, we open the logic app and we're ready to create the workflow. We begin by starting a blank logic app. Instead of using the predefined templates, we look for a Service Bus connector pertaining to Service Bus topics, provide a Service Bus connection name and click Create. And in the connection properties, we set the interval to check for messages every 3 seconds, and we specify which topic and subscription this connector will be listening to. Right, next step, we need to stitch together an email client. We use a Gmail connector. I provide my credentials to authenticate, and then we construct the email. All right, for the body, as I'm typing the message, we want to include the order ID and the status. So we bring in the dynamic context content, which is actually our Service Bus message. We locate the string that imports the content, and we modify to get the properties that we need from the order. So we need the status, and we need the order ID. Let's check the resource group, and we can see the logic app along with the 2 connectors being part of the group. Now let's run the code again and see if the emails are being sent. Let's remember this order ID and wait for the email to be generated. The order has been processed, and nice, the email has come through. Let's open it up. The order ID matches, the status is correct, but the formatting could have been done a little better. We'll fix that later. Let's go ahead and create the next logic app that will handle the insufficient inventory emails. We follow the exact same steps as before. Different name, of course. Select the inventory name and subscription. Now let's create the email. All right, this time we will format the email a little better with some HTML tags. Get the ID first. Okay, save. And we can run the code again. If the order is here, the status is insufficient inventory because I had set the inventory to 0 for one of the products. Waiting for the email, there it is. And we can see that the order ID is correct and that the body of the message is formatted a little better. So let's summarize what we achieved in this section. We created the pay and process the email logic app. We created the insufficient inventory email logic app. We run the code from within Visual Studio, pointing to the functions and services and logic apps on the Azure Portal. And we confirmed that the emails are coming through properly. In the next section, we'll introduce the async request response pattern. Before we begin the next section, let's take a look at where we are in the process. We have successfully implemented the complete process of placing an order and asynchronously processing it through the services and service bus topics. The only indication about the outcome of the order is coming through emails that we generate from the logic apps and we send to the user. Sometimes, however, the requirements of an application may require a real-time response to be sent to the client app that placed the order. This could be achieved by creating a blocking synchronous request, which would require additional HTTP-driven endpoints on the services, one calling the next directly and not through a message broker such as the Service Bus. Although this can be done, it would ignore one of the most important best practice recommendations regarding microservices. To avoid ignoring this important aspect of microservices, we can use the async request response pattern. In order to achieve this, we will modify the order API endpoint to look for a specific flag passed in the HTTP request header. This flag will indicate if the client requires a real-time response. If the flag is there, the order API will programmatically create a transient queue specific to the request and will continue down the normal path of creating the first service bus message. After the message is sent, the order API will wait for a response from the queue, and meanwhile, the messages will continue their trip through the topics as usual. We will also modify the order service update order functions, one for the payment processed and the other for the inventory checked, to place a message in the transient queue, providing the order outcome. The order API that is listening will retrieve the message from the transient queue and will return a result to the client instance that placed a request. And finally, we will modify the client itself to be able to place a request that requires a real-time response. So in this section, we'll develop the async request response pattern. We will modify the order API endpoint. We will modify the order service. We will modify the client console app. We will place an order requiring a response. We will confirm that the client gets a response in real time. And we will confirm that the async messaging route still works. First, we need to install a couple more NuGet packages to the order API. We need the Service Bus management package in order to be able to access the appropriate methods to create the transient queue programmatically. And we will need the Active Directory identity model package in order to be able to authenticate against Active Directory and allow the API app to create the queue programmatically. And now we can begin modifying the orders controller. First, we create a variable to indicate whether the HTTP request contains a property which indicates that the API needs to listen for a response with an outcome to return to the client. So we're looking into the request headers for a flag named implements async request response messaging. If a response is required, then we set the response session ID to the order ID to ensure that a unique transient queue will be created. Basically, the queue will be named the same as the order ID. And at this point, we will need to retrieve a few more connection settings that are required. The subscription ID is the ID of the Azure subscription where our system resides. We also need the resource group name, and the Service Bus namespace. Tenant ID is the ID of the Active Directory instance related to the subscription. Client ID is the ID of the online shop web API applications we will register on the Active Directory. And the client secret is an authentication key we'll generate that will be used as an additional authentication parameter. We'll add placeholders of the same settings in the appsettings.json file, and we'll continue coding and we'll retrieve those values later. So continuing the code, we initialize the rest of the settings variables. Then we create an instance of the authentication context. We will use this to be able to perform operations on the service bus. Then we authenticate against Azure AD and acquire a token. And then we create a service bus. Before we do that, we extract the credentials from the token. And we create a service bus client connection using the credentials. And supplying the subscription ID. All right, so now we are in the service bus, or the program will be in the service bus when this code executes. And the next step is to create the queue, the transient queue. For that, we use an SPQ client object, SPQ object. And we set the appropriate properties of the queue. And then we can create the queue on the service bus, providing the resource group name, service bus namespace, the session ID, and of course the queue parameters. All right, so at this point the queue will be created, and then we create a session client using the same session ID, and we set up a session bridge to the queue. Right. Next, we send the message to the topic client, which is kicking off the normal async process. And right after, we wait for a response from the queue. So instead of saying, okay, we fired the message, let's forget about it. Now we're keeping the orders endpoint open. We're waiting for a message from that transient queue. And when that message arrives, we deserialize the message into an order response object. Which looks like we need to create. So let's go ahead and create the order response model. We need a property to hold the order ID and another property to hold the order status. Continue the deserialization of the response. And finally, we complete the message on the queue so that it can be deleted. And then we delete the queue since this is a transient queue and it has served its purpose at this point. We also close the session client. And finally, we return the result in JSON format to the caller of this endpoint. Make sure everything builds. Okay, now we'll go ahead and retrieve the app settings values from the portal. First, we grab the subscription ID from the subscription. The resource group name is rg-online-shop. The Service Bus namespace, SP Online Shop. For tenant ID, we go to the Azure Active Directory. Under Properties, we copy the directory ID. And we have to create an app registration in Active Directory for our online shop API. And first we'll create for the online shop API running on the local machine. And for that, we need to grab the URL. We'll name that local. Okay, we have registered the application. Now under settings, we can copy the application ID, which is the client ID. Then we need to set up the required permissions to read directory data, save that, and then we can generate a key. We'll name it default key. We set it to expire in 1 year. When we save, we get the key, and it's very important that we copy it because this key will disappear as soon as we get out of the screen. Okay, that's our client secret. Okay, in order to access resources in our subscription, we must assign the application to a role in Active Directory. So we look for that application and we give it the owner role. And the next step is to modify the order service. We begin with the update order inventory checked function. First, we check for the requires response property of the order, and if it exists, we create a response. Then we package the response into a queue message. Provide a message ID and the session ID. Then we create an instance of the queue client. Which is pointing to the transient queue that we had already created from the API. Because we're using the order ID to look for the queue by name. Let's make sure we're using the proper namespace. And then we send the message to the queue. We're going to copy the exact same code and paste it to the update order payment process function. One thing I forgot to do is in the update order inventory check function, I need to check for the order status and make sure that we only send the response back from this function if the order has insufficient inventory. Okay, now we'll go ahead and publish the service to Azure. And let's go to the client console app and examine the changes that I have already made. I added an order response under models. I modified the HTTP request sender to be able to make a request with the HTTP header that indicates that a response is required. And of course, the program class. In the main async method, I display more info to the user about how to kick off an async request versus a request that requires a response. And in the process input method, I split the logic between an async request and a request that returns a real-time order response. Okay, let's make sure the client app and the API are set up as startup projects. Run the code, and we place an order that requires a response. And we have an exception. Let's try to debug and see what's wrong. We'll set up a few breakpoints on the client console app and the API. Debug through, and here we see the exception. Let's see what's going on. Unauthorized code. We look at the content of the response. Okay, so we pointed to the wrong address when we authenticated. Let's go ahead and fix that. We're missing a slash, forward slash. So we'll go ahead and run the code again. The API is running. We'll place an order requiring a response. And we got back a response with the status payment verified. The order ID is 17ED. Let's check the data. 17ED, payment verified. Seems like things are working fine. Now let's place a, there we get the email again. Let's place another order. Make sure the async route is working correctly. So we get back a message from the client app that the order was sent. And the difference here is that this message we're getting back from the response that the order has completed, and we get back the status. So this one starts with 5E37. Let's check the data again. 5E37. So the async route works as well. And there's the email. Okay, now we'll go ahead and publish the API to Azure. And now that the code has been published, we must make sure we have the appropriate app settings. These are the new app settings that we entered when we started creating the async request response pattern. So we enter the same one here. And we create another app registration for the live app in Azure Active Directory, since the URLs are different between the local host and the one on Azure. We'll name this one live. Go grab the URL. Create a new key. Grab the secret and the application ID and enter it in our settings. Save everything. And we shouldn't forget to specify a role for the live application in Active Directory. Okay, so we're back in Visual Studio and we have deployed the order API. Let's make sure we have our startup projects properly configured. So we'll just set the client as our startup project. And that's the only project we're going to run locally. Everything else will be running on Azure. go ahead and place the order. Got back a response. The ID is F812. There it is, we have it here, so it worked. And now let's demonstrate something else, and there's the email again. Let's demonstrate how the queues that we're creating from the API are transient, and once the message, so they're created, and once the message is processed, they are deleted. So in order to do that, we place another order, and before we place the order, right under queues, we can see that there are no queues. So we'll go ahead and place the order. As soon as we place it, we'll refresh here. We see that the queue has been created, and this actually is the order ID, and we can confirm that. D9E. Okay, now we got a response back, and by now the queue should have been deleted. I'll refresh again, and there we can see that the queue was deleted. So let's recap what we did in this section. We developed the async request response pattern, and to do that, we modified the order API endpoint. We modified the order service. We modified the client console app. We placed an order requiring a response. We confirmed that the client gets a response in real time. We confirmed that the async messaging route still works. And in the next section, we will create a wiretap. In this section, we will create the wiretap. We will explain what a wiretap is. We will review the code. We will demonstrate the wiretap working, and we'll actually see the messages going through each topic. We will demonstrate multiple clients placing requests and make sure that each client gets back the appropriate response. And as bonus, we will demonstrate remote debugging capabilities from Visual Studio to code running on Azure. So I went ahead and created the wiretap console app, and we will examine what the code does. A wiretap basically is an application, in this case a console app, that we can use to monitor the messages on the topics in real time. And this could be useful for when you're developing an application, but also when your application is running on production and there are issues with the messages somewhere and you don't know exactly where. You can fire up one of these wiretaps and do some test runs and see how the messages go through the topics and possibly figure out where the problem is. So first thing to know is that in order for our code to work, we had to install a few NuGet packages. And those NuGet packages are the Microsoft Azure.management.service bus, Microsoft.Azure.service bus, Microsoft.extensions.configuration, Microsoft.Windows Azure.configuration manager, and Newtonsoft.json. So if we look at the program class, so first I create 4 static variables of type iSubscription client, and each one of those corresponds to a topic we have on the service bus. Then we create variables for the application settings, and these are the same app settings that we've used in other projects in this solution. Then in the main async task method, first we create a variable of a wiretap ID, which we will use in order to generate unique subscriptions. So that's a GUID. Then we authenticate on Active Directory, and we get the token credentials, and create a Service Bus management client with those credentials. Then we create the subscription parameters for a subscription, and these will be the same parameters for all these subscriptions we're going to create. So basically what we'll do next is we're going to create 4 subscriptions, one on each topic that we mentioned before, and those will be transient subscriptions. And those will listen for messages that come into the topic, and because they will not be filter subscriptions, they will get all messages that come to each topic. So that's what we do. You see these 4 lines here. We create those 4 subscriptions, and it's the same parameters that we've used before to create a subscription or a queue. We need the resource group name, the service bus namespace, the name of the topic, and a unique name for each subscription, and of course the subscription parameters. And this is where the wiretap ID comes into play. Each topic can have a subscription with a unique name. Okay, now that we have our subscriptions created, we create 4 subscription clients to be able to listen to those subscriptions for messages. And after we create the subscription clients, we call 4 methods that register a message handler that will receive messages from those subscriptions. And those message handlers receive messages continuously from the Service Bus topic. And when we register a message handler, a new thread will begin and it will start receiving messages. So the register, let's look at one of them because all of them are the same. Register, create order on message handler, and receive messages. This method creates a message handler options object. We specify the exceptions receive handler in order to process any exceptions that might occur from listening to the messages. We provide a couple of properties, the maximum current calls and autocomplete. And finally, we register a delegate method in order to process the messages that are coming through the topics. That method that we register here is process create order message async. So this method that is constantly listening for messages on the topic, it grabs the topic message, it serializes it into an order object, and then it writes a line showing that the create order topic received an order with a specific ID. And then finally, it completes the message on the subscription client so that the message is not picked up and processed again. And we repeat this registration of handlers and processing of messages 4 times, 1 for each topic. That's about it. And now we can go ahead and run it. Of course, in our solution, we have to make sure that we have the appropriate project starting up. So we have the wiretap and the client. Everything else is running on Azure. So we'll go ahead and run the program. We see that both console apps are starting. Here at the top, we have the client where we can place our orders. And at the bottom, I will place the wiretap application so we can see the messages as they go through the topics. Okay, let's place an order that requires a response. Make sure I provide the right command. Now look at the wiretap, the messages to start coming through, and there they are. We see 4 topics, which is what we expect, and we got a response back, and the order IDs match. Now there's one more thing I want to demonstrate. So we want to make sure that each client gets its own response back, and we don't mix up the responses if we have multiple clients. So in order to do that, demonstrate that, we'll go into the bin folder of the online shop client, and here's the email too, and we'll fire up more instances of the client. Let's do 2 more. Minimize the windows so that we can fit them on the screen. Okay, so we will place another order here. I will not place it yet. I'm going to type the commands first on all windows. One here. And then I'll quickly place all three of them. And we see how fast the topics are receiving the messages. And we can examine the order IDs. So this client sent the order with ID 0 that starts with 051, and it received back 051. And all of them, as you can see, receive back the proper order in the response. And then those are the 3 emails that we expected to get from those 3 orders. So yes, this demonstrates the usage of a wiretap to monitor the Service Bus topic messages. As a bonus material, before we conclude this screencast, I would like to demonstrate how well Visual Studio is integrated with Azure Platform as a Service services. So let's assume the scenario that we have deployed our application to production and we have introduced a bug. Well, it would be nice if we could debug the actual code on Azure and see what is wrong on the actual code that is running on production. Turns out that we can easily do that with Visual Studio. First, we need to go to our debug options here and make sure that under debugging general, the enable just my code checkbox is not selected. Then we can start the application. We notice that only the client is running locally, everything else is on Azure. Here on the left side, we have the Cloud Explorer. And when it opens up, if you have not used that before, you will see the Visual Studio Professional. This is my subscription. And we see that we have only one resource group. Under our resource group, we see all our resources. Let's assume we have a problem with the order service. We'll right click on that and say attach debugger. We'll go ahead and place a breakpoint right here. This is in the update order inventory checked function. It's going to take some time to establish a connection to Azure and attach a process that we can debug. There it is, our function is running. And we'll go ahead and place the order. It's still loading symbols. We place the order from our client running locally. And we can see that the breakpoint actually works, and this is the code that we have on production, and we can use it just like if we were debugging locally. So we can browse the properties, see what values they have. Meanwhile, because this is an async process, this has continued, this has completed the order, because we're just looking at the update order inventory checked, which does not block the order from completing. And then here we can step through. Of course, this will not be true because the status was sufficient inventory or verified, and we will transfer to the next point. And we can continue debugging here. And that's it. This demonstrates how tightly Visual Studio is integrated with Azure and the flexibility and power that it provides us with. So in this final section of this screencast, we explained what a wiretap is, we reviewed the code, we demonstrated the wiretap working, we demonstrated multiple clients placing requests and each client getting back the appropriate response, And we demonstrated the remote debugging capabilities of Visual Studio while we were able to debug a function that was running on Azure. We have reached the conclusion of this screencast. Let's recap some important areas that we have covered. We explored what a microservices architecture is and the problems it solves. We developed a solution based on an Azure PaaS Microservices architecture. We demonstrated usage of web apps, Azure Functions, Logic Apps, Azure Service Bus, and Azure Tables. We demonstrated usage of the Azure Portal. We implemented the async request response pattern of microservices. We demonstrated Azure PaaS deployment from Visual Studio. We developed a wiretap application that monitors Service Bus topic messages. We demonstrated programmatic creation of Service Bus queues and topics. We demonstrated programmatic Azure Active Directory authentication and manipulation of Azure resources from an app. And we demonstrated Visual Studio remote debugging capabilities. As a reminder, all the code developed for this screencast can be found in this GitHub repository. I hope you enjoyed this exercise and found the topics we covered useful. Please visit my YouTube channel periodically as I intend to continue exploring exciting technologies related to Azure.